time now because it's always broken. All right, class.
Yes.
Thank you, thank you, thank you. Where were you on that one? I didn't hear you. Thank you. All right, good. All right, so we're actually doing derivative as a function. So this is actually, again, the big topic when we do calculus. It is limits, continuity, and derivatives to go along with this. So we're going to define derivative, graph derivative, and identify where a function has no derivative. So what this is, right here, that's my f prime of c. That means I'm taking the derivative of the function f, which was the same thing as taking the limit, or, you know, x plus h. But in this case, it's going to be c. Where we're doing all that, find the derivative of the function f of x equals x squared minus 5x at any real number c. Now, let's do the voodoo. So f prime of x is equal to, now let's see if you paid attention to the voodoo. What's going to happen to that x squared? What do I do with the number in front?
And the 1. So
Yeah, it's a 1, right?
2.
So it's going to be a 2 times 1. So that's going to be 2. And then there's my x. What do I do to my variables? 2 minus 1, which gives me 1. So it's just x to the first, right?
Yeah.
Good. So we can put x to the first here if you want to, but it's fine. Now, what about the negative 5x? Negative 5x.
No exponent.
There is no exponent, or there is an exponent, and the exponent is?
0.
Nope, try again.
1.
It is 1.
Okay.
It is 1. So the exponent's going to be 1. So what am I going to do with that 1?
Multiply
Multiply
over
it to the negative 5, so negative 5 times 1.
negative 5.
And what's going to happen to my, that's going to be x to the,
0 power.
x to the 0. So when it becomes x to the 0 power, anything to the 0 power is?
0. 1.
1.
Okay.
Anything to the 0 power is 1. So that means that it's still going to have my negative 5, right? So it's going to be negative 5 times 1, which is just negative 5 there. So that's it.
Yay.
That is the derivative. So that's going to give me the slope of the tangent at any real point. I can just plug in any x value in which that it is continuous or it is derivatable. You can take a derivative there, or it's, I hate even trying to say it. I can take a derivative, so it's derivative. Derivable? Yes, derivable. There it is. Okay, different accent. All right, so there we go.
Say derived.
Yep. So, wow, with me slurring this much, I must have been drinking and deriving.
My God, Pajo.
See what I did there?
Damn it,
Drink
Pajo.
and derive.
Very sure.
Pa-da-ting.
There
There we
you go.
go. All right. So let's rewrite this one right here. So we're going to differentiate this one right here and then determine the domain of f prime. Domain of f prime. Okay. So first, I'm going to rewrite this. So f of x equals x to the what? What am I going to rewrite that as?
X.
1/2, right? Yes?
I thought it would be negative 1/2.
Nope. Negative 1/2 would mean that it is in the denominator.
Okay.
It would be in the denominator, right? So let's go ahead and do the math now. So from here, having my exponent as a fraction, it makes life a little bit easier. So now I could say f prime of x is equal to, what number is in front of the x? What is the number in front?
1.
1. 1 times
1/2.
1/2 is?
1/2.
Very good. X. Now what am I going to do to that 1/2? Yes, very good. So do the math, minus 2 over 2, like that, right?
Mm-hmm.
Which is going to give me a
Negative 1/2.
negative 1/2. And then I'm going to clean it up. So that is the derivative. But now I want to clean it up. So I am going to move my negative exponent here, I'm gonna move it to the denominator. So that's gonna change 1 over 2 to the x positive 1/2. And then I'm gonna rewrite it, so instead of having my exponent a 1/2, I'm gonna rewrite it, because I'm hoping you guys could actually see here. You can see this a little bit clearly now. Because I want to find the domain of this. What can I not have in the domain? Or, I'm sorry, what can I not have there? Because I have a radical. Nope. This radical right here in the bottom. It's important. What can I not have inside a radical? What numbers can I not have there? I cannot have negative, right? So because of that, I know that my x has to be greater than what?
Negative infinity.
Nope, greater than 0, right? Okay, has to be greater than 0 because there is a square root there. Now, if it is 0, can it be equal to 0? Can x equal 0?
No.
What is the square root of 0?
0.
0. What is 2 times 0?
0.
Can I have 0 in the denominator? It's undefined. I cannot have 0 in the denominator. So I know that x has to be greater than 0, but it cannot be equal to, right? So I have to keep that symbol like that. I don't, I just tested it for 0 to make sure. So let me see. The domain of this is going to be anything that now satisfies this. So the domain is going to be x greater than 0. Or, okay, as interval notation, I would start with a parentheses, 0, comma, and that goes to positive infinity. And then there is set builder notation. So you might see this also. X such that x, all real numbers, or
Is that called a bracket?
nope, brace.
Oh, okay.
Just think of someone wearing braces and it's like a little squiggly, metal bracket, right? It's a squiggly bracket, it's braces. So, set builders. So x such that, that's a line going straight down. Okay? Line going straight down. X such that x is, x, all real numbers greater than 0. So you could see it either way, but I normally like interval notation with the parentheses, 0, comma, infinity, parentheses. I normally prefer that. That's my favorite. But you're going to see all methods. Make sense? Is that nonsense? A little bit nonsense? Are you okay? Guess who gets to do the next one by themselves? Guess who's coming up to the board for the next one? Interpreting the derivative as a rate of change. The surface area S in square meters. Okay, that's important. Units are super important on these ones. Of a balloon expanding as a function of time in t seconds according to S equals S of t. So it's my function in terms of time. That's what that means. The function S, surface area, in the terms of t is equal to 5t squared. Find the rate of change for the surface area of the balloon with respect to time. What are the units of S? Now, it's a rate of change. So, let's do S prime. That's supposed to be an S, and that one is not an S. There you go. S prime of t. So, let's take the derivative. 5t squared, so that's going to give me what? Give me the derivative. 5t squared. What are you gonna do with the 5 out front? What? By 2, very good, so that's gonna give you 10t, right? Okay, just 10t, no t squared? Yes, good, that's it. So it's gonna be 10t. See, knew you could do it. Now, this is a rate of change. Just like Denny yesterday driving through that, school zone, right?
Tell another kid again?
No, same one. Remember, this is Exhibit A of his murder trial. Okay, so the rate of change. What units? Because S is the surface area in what? Remember, Denny's murder trial, it's going to say that he was doing 60 miles an hour. His rate of change means his speed when he hit the kid in the school zone, in the crosswalk. Okay? It's funny because you dodged the guy with the stop sign. You dodged that guy, didn't you? Yeah, it's crazy. Okay? Anyway, so what are my units? Just remember, okay? Denny, school zone, miles per hour, right?
Miles per hour per 5 minutes.
This one's going to be
Square meters.
meters squared, right? Meters squared. Remember, it's a rate of change
In seconds. So meters.
per second. So every time that you guys are thinking about this, think of Denny driving through that school zone. He's doing miles per hour. That is his rate of change. Miles per hour. Meters squared per second. So every second that we are going to increase, my value is in meters squared, right? It's an area around the surface of that balloon, right? Does that make sense? Hopefully, yeah?
Yeah.
Good? Just always think about Denny driving to that school zone, okay? Everyone's gonna think about
It's
that
in
too.
physics.
Yeah. And hold on, let me see. How many more do I have?
You have a lot. You have like 3 pages, like 6 slides.
No, I'm just trying to see which ones I want to do. I think I'm gonna leave off here. I'm gonna leave off here for today, for right now. I'm gonna pick this up later, but I want you guys actually working on doing more of these problems with the derivatives, because these ones right here are its own monster. Okay, so I need you guys to actually do the derivatives first, and then we'll come back to this. So make sure you all like, share, and subscribe. Hit that notification button. Support my channel. Buy stuff from the merch store.